Hello students. Good morning. Today I am here with you with marathon of part 2 of chemistry. So yesterday we have completed part 1. Then this 3 to 4 hours we are going to just take the glimpse of all the reactions which comes in part 2, and it helps for your revision also. So without wasting time, let us start from the chapter haloalkanes and haloarenes. Okay, what are these haloalkanes? To be very quick, we have alkanes with the general formula R group attached to hydrogen. If I replace one hydrogen or one or more can also be replaced. If I replace one or more hydrogen of alkanes by any halogen, we get, in the place of this one we have to add halogen, we get alkyl halides, or they are also called haloalkanes. Okay, here X can be fluorine, chlorine, bromine, iodine, like this. It can be any halogen atom. Minimum one you have to remove, one hydrogen from hydrocarbon we have to remove, and we have to add halogen in the place of that one. So more than one also you can substitute. Next, if I come to haloarenes, haloarenes are the one you are going to substitute hydrogen of benzene ring, that's arene, by halogen. Example, we have C6H6 benzene. One hydrogen or more hydrogen can also be replaced. It is replaced by halogen. We get C6H5 X. Here X may be fluorine, chlorine, bromine, iodine, like that. Okay, so they are nothing but haloarenes. Now we have one more, that is aralkyl halides. What is the meaning of aralkyl halides? Aryl alkyl halides. When benzene ring is attached to any alkyl group, let me consider CH2, and that is attached to any halogen. These type of compounds are called aralkyl halides. I think there's no doubt in this basic things. Now let's go for classification of alkyl halides, haloalkanes and haloarenes. Based on number of halogen atoms present, these are classified into monohaloalkanes or monohaloarenes. The first classification is based on number of halogen atom. If only one halogen atom is present, then it is called monohaloalkanes or arenes. Monohaloarenes. Example, and take any alkane, replace one hydrogen. I'll take ethane. In ethane, I am going to replace one hydrogen by halogen, C2H5 Cl. Only one halogen is present. This is example for monohaloalkane. Monohaloarene, benzene ring attached to any halogen atom. You can take chlorine also, or generally you can write X also. So that is monohaloalkane. First classification is based on number of halogen atom. Monohaloalkane or dihaloalkane. Di means two. Dihalo compounds. Dihalo compounds, two halogen atom will be there. Two hydrogen atoms are replaced by two halogen atoms. Then they are called dihalo compounds. Here I have one thing. If in case both the halogen atoms are present on same atom, imagine we have CH3, CH, halogen, halogen. If both the halogen are present on same carbon atom, then they are called geminal dihalides. What is the name given to them? The name is geminal dihalide or geminal. Geminal dihalide. And if halogen atoms are present on different carbon atom, like this adjacent carbon atom, CH2, single bond CH2, Here, this is also attached to one halogen, and this carbon is also attached to another halogen. These type of compounds where two halogen atoms are attached to adjacent carbon atom are called vicinal dihalides. Vicinal dihalides. So monohalo compounds, dihalo compounds, monohalo means single halogen, di means two halogen atoms. If both the halogen atoms are present on same carbon atom, then they come under the category geminal dihalides. Simply it is represented as gem dihalide also. And if both are present on adjacent carbon atom, then they come under the category vicinal dihalide. And in aromatic compounds also I can write example of vicinal dihalide. Benzene ring, where adjacent carbon atoms are substituted by halogen. This is also example for vicinal dihalide. Okay, so this is geminal dihalide. So this is about dihalo compound. Next comes trihalo, polyhalo. Trihalo means three hydrogen atom is replaced by halogen. Polyhalo means many hydrogen atoms are replaced by halogen atoms. So that is the first category based on number of halogen atoms present. Next we have based on hybridization of carbon. Halogen can be attached to sp3 hybridized carbon also, or it can be attached to sp2 hybrid carbon also. In sp3, if halogen is attached to sp3 hybrid carbon atom, here I'll write the example. You should tell the difference. First thing I'm writing CH3, CH2, X, and another one I'll take CH3, CH, CH3, X, and one more is CH3, C, CH3, CH3, X. See these three example here. What difference can we observe? In all these three, halogen is attached to sp3 hybrid carbon atom only. But what is the difference? In first case, halogen is attached to primary carbon atom. Primary carbon atom is the one which is attached to only one other carbon atom. So this is called primary alkyl halide. This is primary alkyl halide. If halogen is attached to primary carbon, it is primary alkyl halide. And in second case, halogen is attached to which type of carbon atom is this? Carbon attached to two other carbon atoms. So it is secondary carbon atom. So this is example for secondary alkyl halide. Secondary alkyl halide. And last one, halogen is attached to tertiary carbon atom. Tertiary carbon atom is the one which is attached to three other carbon atoms. Here this carbon is attached to three other carbon atom. So this is example for tertiary alkyl halide. In all these three cases, halogen is attached to only sp3 hybridized carbon atom. And next, in this example, let me take ring like this. Yes, here. What is the name given to this? Here halogen is attached to sp3 hybridized carbon atom, but that sp3 hybridized carbon atom is adjacent to sp2 hybrid carbon atom. Okay, this carbon contains double bond which is sp2 hybridized, and that is attached to sp3 hybrid carbon atom, and on that sp3 hybrid carbon atom we have halogen atom. These type of alkyl halides are known as allylic halide. These are called allylic halides. And next one, if you take benzene ring, and for that alkyl group is attached. Above one is not benzene ring. Here it is benzene ring, CH2, X. See, This position is called benzylic position. That position is called, the very next position to benzene is called benzylic position. Halogen is attached to benzylic position, benzylic carbon atom. That's why the name given is benzylic halide. Benzylic halide. In all these three cases, in all these cases, halogen is attached to sp3 hybrid carbon atom. I hope this one is clear. Next, let us go to halogen attached to sp2 hybrid carbon atom. Here, take this one example. Need not to take ring. You can directly take open chain also, like this. CH2 double bond CH X, like this also. Here halogen is directly attached to sp2 hybrid carbon atom. These type of halides are called vinylic halide. Vinylic halides. These type of halides are called vinylic halides. Okay, and next one we have is take the example of halogen directly attached to benzene ring. If halogen is directly attached to benzene ring, then they are called aryl halides. Aryl halides. These are the main, this is the main classification of haloalkanes and haloarenes, that is halogen substituted compounds. Next, let us go to methods of preparation of alkyl halide. First method of preparation of alkyl halide is by free radical halogenation. Free radical, you have studied this reaction in 11th standard. So how do we take this one, free radical halogenation? Take any one alkane. I'll take methane, CH4. It is treated with halogen in the presence of sunlight. In the presence of sunlight, or you can heat it also. When alkanes react with halogen in the presence of sunlight, then we get monosubstituted, disubstituted, trisubstituted, or tetrasubstituted compound along with HCl. See, here we are getting mixture of mono, di, tri, tetra halo compounds. That's why we usually don't prefer this method. Since we are getting all different types of halides together, we don't get only one type of alkyl halide. So again, we need to do the separation technique. So this method is not usually followed because of getting mixtures. Next is from alkene. Alkenes means they contain double bond. Here we have two methods of preparation. See, first one, if I take alkene and add hydrogen halide, CH2 double bond CH2 ethene. When it reacts with hydrogen halide, what happens? Double bond will break, hydrogen will be attached to one carbon atom, and halogen goes and attaches to another carbon atom. We get CH2 single bond CH2. This will be attached to hydrogen, and one more bond will form with carbon and halogen. So this is addition of hydrogen halide. Here one thing is, this is symmetrical alkene. Symmetrical means on either side of the double bond we have same group. See, on both the sides it is CH2 CH2. Wherever you add hydrogen, wherever you add halogen, it will not make much difference. But when I consider propene, CH3 CH double bond CH2. Here, when this one reacts with hydrogen halide, what happens? See, in this case, what I get is, this is unsymmetrical one. So hydrogen, the positive part of the reagent, here hydrogen gets partial positive charge, halogen gets partial negative charge. Positive part of the reagent will be attached to carbon containing more number of hydrogen. In this double bond, check which carbon contains more number of hydrogen. This carbon. So positive part of the reagent will go and attaches to carbon containing more number of hydrogen. It will go and attach that, and here negative part will be attached to carbon containing less number of hydrogen atom. So this is what happens. And what product do we get here? CH3, CH, X, CH3. Okay, so this rule is called Markovnikov's rule. But if I take peroxide, then halogen will go and attach to last carbon atom. This is anti-Markovnikov's rule that occurs in the presence of peroxide only. Without peroxide, this Markovnikov's rule is followed. This is one method of preparation from alkene. Next method is addition of halogen, direct addition of halogen, not hydrogen halide. If you take alkene CH2, double bond CH2, and treat it with bromine Br2 in the presence of carbon tetrachloride CCl4. We have two bromine atoms, one will be attached to one carbon, another one will be attached to another carbon, and double bond between them breaks. We get CH2, single bond CH2, Br and Br. So this is how we get haloalkane from alkenes. One is addition of HBr, another one is addition of Br2. This is one test for unsaturation also. This is test for unsaturation. That's called actually bromine water test. Here, in the presence of bromine water, if double bond is present, the discharge of reddish brown color of bromine water takes place. So that indicates the presence of alkene. Next method is preparation from alcohol. There are different methods of preparation of haloalkanes from alcohol. Let us study them one by one. First method of preparation is by treating them with HCl in the presence of anhydrous ZnCl2, anhydrous zinc chloride. Alcohol react with HCl in the presence of anhydrous zinc chloride to form RCl along with H2O. This is a test for determination of primary, secondary and tertiary alcohol also. See, this RCl, alkyl halide formed, is insoluble in water. It forms a precipitate. If tertiary alcohol is present, then immediate turbidity occurs. If secondary alcohol is that, then turbidity will occur after 1 or 2 minutes. And if primary is that, it produces turbidity only after heating. So this is one of the tests to distinguish between primary, secondary and tertiary alcohol also. And this reagent, mixture of HCl and anhydrous zinc chloride, is called Lucas reagent. This reagent is called Lucas reagent. And what is the use of Lucas reagent? It distinguishes between primary, secondary and tertiary alcohol. Now let's go to next method. Next method is when alcohol is treated with NaBr in the presence of sulfuric acid H2SO4, we get alkyl bromide RBr plus NaHSO4 plus H2O. Okay, alkyl bromide RBr will be obtained with reaction on reaction with NaBr. And when alcohol is treated with PCl3, here we get RCl plus H3PO3. How to remember this? See, we have RCl, ROH. This is for above one, okay? ROH, ROH and ROH. This reacts with PCl3, PClCl, Cl, PCl3. This one will be removed. What's the byproduct we have written here? H3PO3, right? H3, 1, 2, 3, PO3, or POH thrice also you can write, and RCl3, RCl will be obtained. This is how you can remember the product here, byproduct. Okay, next one we have is reaction with, here halogen can be chlorine or bromine. Okay, so either you can take chlorine also, or you can take bromine also. With bromine also, same reaction will takes place in this case. And next one is reaction with PCl5. With PCl5, see how reaction occurs. We have ROH PCl5 is that, right? Right, like this, PCl3, Cl and Cl, total PCl5. Break the bond like this, and three different products are formed here. Tell me the name of the products. First one is RCl plus POCl3 plus HCl. Okay, like this in short method you can remember. No need to by heart all the products. Just if you remember like this, it is very easy. Next one is, after this you can directly heat this alcohol with red phosphorus and halogen. The halogen here can be bromine or iodine. X can be bromine or iodine. We get direct alkyl halide. Alkyl halide formation takes place. When alcohol are treated with red phosphorus, we get only alkyl halide product. And last is reaction with SOCl2 in the presence of pyridine. In the presence of pyridine, it reacts with SOCl2C. This is also again the same case. ROH SOCl and Cl. Break the bond like this. Tell me the different product which you get. RCl plus SO2 plus HCl. Here the two products obtained are in gaseous state. That's why we get only pure alkyl halide. That's why this method is preferred. So these are different methods of preparation of haloalkanes from alcohol. Next is halogen exchange method. Halogen exchange method means halogen will get exchanged between two compounds. First reaction we have is Finkelstein reaction. In Finkelstein reaction, we'll be having alkyl halides. Alkyl halide, that may be alkyl chloride or alkyl bromide. It is treated with sodium iodide. It is treated with sodium iodide in the presence of dry acetone. In the presence of dry acetone. Halogen exchange. So alkyl group and sodium, they exchange the halogen. We get alkyl iodide along with sodium halide. NaCl or NaBr formation takes place. So Finkelstein reaction is used in preparation of alkyl iodide. Remember this. And one more reaction here we have is Swartz reaction. First I'll write the Swartz reaction. In Swartz reaction, alkyl halide will react with halogen, may be here also chlorine, or it can be bromine. It reacts with inorganic fluoride. I am taking silver fluoride. I'll take AgF. You can take cobalt fluoride or mercury fluoride, or you can take any other inorganic fluorides. Okay, all inorganic fluorides, they form alkyl fluoride plus AgX. Okay, so one thing to remember is in Swartz reaction we are getting fluorides. In Finkelstein we are getting iodide on alkyl group. So F does not form. Finkelstein does not contain fluorine. Like that, you remember, it's crisscross like this. So Finkelstein, iodine will be substituted. Swartz, fluorine group will be substituted. So these are different methods of preparation of alkyl halides. Next is methods of preparation of aryl halide. So we have direct halogenation of benzene. Benzene undergo substitution reaction, that is electrophilic substitution reaction, when benzene is made to react with halogen, that is either it can be chlorine or it can be bromine. In the presence of FeCl3, halogen will be substituted to benzene ring. In any position, all are equivalent position, any one of the position, halogen will get substituted. This is direct substitution of halogen to benzene. And second method of preparation is from benzene diazonium salt. Do you know the structure of benzene diazonium salt? Yes, we already know the structure of benzene diazonium salt. So what is diazonium salt? How do we prepare diazonium salt? Aniline, NH2, is treated with NaNO2 in the presence of HCl. The temperature should be 0 to 5 degrees Celsius. This leads to formation of benzene diazonium. This N2 group is called diazo group, N2 plus group, chloride. Benzene diazonium chloride salt formation takes place. This benzene diazonium chloride, on further treatment with, say this is stable only at lower temperature. At higher temperature, this undergoes dissociation. That's why we maintain the temperature at 0 to 5 degrees Celsius. When benzene diazonium chloride is treated with cuprous halide, either if you treat it with Cu2Cl2 in the presence of HCl, Cl group will be substituted. Concentrate on this reaction. These are important reactions. What do we get? Cu group will be substituted on benzene ring along with, sorry, not Cu, Cl group will be substituted on benzene ring. Liberation of N2 gas will take place. If you treat benzene diazonium salt with Cu2Br2 in the presence of HCl, here Br will be substituted on benzene ring. Br will be substituted with liberation of N2. These reactions are called Sandmeyer's reaction. What is the name for this reaction? Name is Sandmeyer's reaction. Sandmeyer's reaction. What is Sandmeyer's reaction? Benzene diazonium salt treated with cuprous halide in the presence of HCl. In the presence of HCl to give halogen substituted benzene ring. Halogen will be substituted directly to benzene ring. These reactions are called Sandmeyer's reaction. Okay, here we have substituted chlorine and bromine. For iodine, direct substitution, directly treated with potassium iodide. If you treat this one with potassium, benzene diazonium salt is treated with potassium iodide, we directly get iodobenzene. Iodine will be substituted along with N2 plus KCl. Byproduct formation takes place. And last one, the substitution of fluorine. How fluorine can be substituted on this benzene ring with benzene diazonium salt? We have to treat benzene diazonium salt with NaNO2 in the presence of HbF4. So this forms fluorobenzene. Fluorine group will be there along with N2 plus NaCl. Different byproducts will be formed, BF3. So these are different ways in which we can synthesize haloarenes. First one is direct substitution of halogen. Another one is we have to prepare benzene diazonium salt. From benzene diazonium salt we can continue. Next is physical properties of alkyl halides. Lower members are gases. We have lower members as gases, and if I go to higher members, they exist in liquid state as well as in solid state, and they will be having all these are sweet smelling liquids. Higher members are sweet smelling liquids. Okay, and if I consider their solubility, are they soluble in water? No, they are insoluble in water. Insoluble in water. Alkyl halides are insoluble in water, but they are soluble in organic solvents. That is, they are soluble in non-polar solvents. And what about higher boiling point? As the number of carbon atom increases, boiling point also increases among this. They will not form hydrogen bond with water. That's why they are insoluble, and they will not make hydrogen bond with themselves also. So compared to alcohol, their boiling point will be less, but as the number of carbon atom increases, their boiling point also increases. So this is about some physical properties of alkyl halides. Next, let us go to chemical properties. If I consider alkyl halide bond, what is the nature of alkyl halide bond? Carbon halogen bond. Carbon is electropositive and halogen is electronegative in nature. So carbon gets partial positive charge and halogen gets partial negative charge. So whenever nucleophilic substitution takes place, nucleophile means nucleon loving species. It is rich in electron. So where nucleophile will substitute, it gets substituted on carbon, nucleon, positive charge loving. In case of alkyl halide, positive charge is present on carbon atom. That's why nucleophile will attack on carbon atom. Remember this. So nucleophilic attack will take place like this. Nucleophile will come. I'll represent nucleophile like this. And when it reacts with alkyl halide, it forms nucleophile will get attached to carbon, and leaving group, that is halogen, will leave the molecule. And we are going to study some of the nucleophilic substitution reaction of alkyl halide. As I go on telling the reagent, you should start writing the answers for that one. Okay, first one is reaction with aqueous KOH. With aqueous KOH, which is nucleophile here. OH minus is nucleophile. With aqueous KOH, what product will be formed? ROH. OH is nucleophile. OH minus, that will go and take the position of halogen. We get ROH along with KX. And if I treat it with NaO R dash, we get ether. R dash O minus is the nucleophile, so which attaches in the place of halogen, and we get R O R dash along with NaX. If you know which one is the nucleophile in the given compound, you can easily predict the product in this case. And if we treat alkyl halide with NaSH, here we get RSH along with NaX. This is called thioalcohol, and RSH is called thioalcohol. Above one is ether. Above that we have alcohol. Okay, and next one we have is reaction with KCN. alcoholic KCN, all with alcoholic KCN. CN minus, yes, we get RCN, that is alkyl cyanide formation takes place along with byproduct. And if I treat it with AgCN, see, with AgCN it forms RNC, isocyanide formation takes place. With KCN it forms RCN, with AgCN it forms RNC. This is because KCN is ionic in nature, whereas AgCN is covalent in nature. We get RNC plus what is the byproduct form? AgX will be formed. This is the byproduct. And next is reaction with AgNO2. Alkyl halide reacts with AgNO2. What is the product? NO2 minus is nucleophile, which forms RNO2 plus AgX. And last one is not last one, we have KNO2 also. With KNO2 again it's RONO. With AgNO2 we get nitroalkane, but with KNO2 what we are getting? Alkyl nitrate. Okay, alkyl nitrate we are getting RONO. Alkyl nitrate formation takes place, whereas in above case nitroalkane formation takes place. Okay, remember this one. I'm writing star mark on this. These four. Remember these four reactions which are important one. Next we have is last one, reaction with RCOO AG. Here we get, take R dash so that there will be no confusion. We get R dash COO, R will be obtained along with formation of AgX. These are all different nucleophilic substitution reactions of alkyl halide. Okay, so that's about nucleophilic substitution reactions of alkyl halide. Next we have a C. This nucleophilic substitution reaction occurs by two mechanisms. Two types of pathways are there. One is SN1 mechanism, another one is SN2 mechanism. So let's study the difference between SN1 and SN2 mechanism. We know SN1 mechanism is unimolecular. That means it is of first order reaction. Sorry, this is of first order reaction. And what about SN2? It is of second order. Second order, it follows second order kinetics. That is the first difference between SN1 and SN2. So this SN1 is generally carried out in polar protic solvents. Generally, SN1 is carried out in which type of solvents? Polar protic solvents. Whereas when I come to SN2, it is carried out in polar aprotic solvents. Can you give example for polar protic and polar aprotic solvents? Aprotic solvent. Polar protic solvents are water, alcohol, acetic acid. All these are polar protic solvents. Polar aprotic solvents, DMSO, very good. DMSO, then DMF, acetonitrile, acetone. All these are example for polar aprotic solvents. Okay, so this is second thing. And if I consider reactivity of the alkyl halides, in case of SN1 reaction, tertiary alkyl halides are more reactive than secondary, which is more reactive than primary. Then comes CH3. Okay, then comes CH3, that is the one with lowest reactivity. And if I consider SN2 mechanism, here CH3 is reacts faster compared to primary, secondary, that is methyl group, compared to tertiary. This is the order of reaction of alkyl halides. And in case of SN1, there will be formation of carbocation. Intermediate formation takes place. Sorry, there will be no intermediate formation here. Intermediate formation takes place. That means carbocation will be formed in SN1 mechanism. And if I consider SN2 mechanism, so there will be no intermediate formation. Here we get a transition state, but we cannot consider that one as intermediate. Okay, next we have is change in configuration. Here we get configuration is retained, that is racemic mixture will be formed. Racemic mixture, half 50% inversion, 50% retention will be there, so which forms a racemic mixture. Whereas when I come to SN2 mechanism, here inversion in configuration takes place. Inversion in configuration will be there in case of which one? In case of SN2 mechanism. So these are the certain differences between SN1 and SN2 mechanism. Next, let's go to different definitions. Dextrorotatory. See, these are some optically active compounds will be there. If the optically active compounds rotate plane polarized light towards right side, dextro means right, dextra means right. If they rotate plane polarized light are rotated towards right direction. Right means clockwise direction, then they are called dextrorotatory. If the compounds rotate plane polarized light towards left side, then they are called levorotatory. Levo, left, L for left, remember like that. So if the compounds rotate plane polarized light towards right side, then they are called dextrorotatory compound. If the compound rotate plane polarized light towards left side, then they are called levorotatory compound. And if I have 50% of dextrorotatory and 50% of levorotatory, then optical activity will be zero. They'll get cancelled out, and that mixture, equimolar mixture of D and L isomer, is called racemic mixture. And next we have a chiral compound. Chiral means asymmetric. If carbon is attached to 4 different groups, A, B, C, D. Okay, carbon is attached to 4 different groups, then we call such type of carbon as chiral carbon, which is represented with the asterisk mark, and that compound is called chiral compound. Okay, if the compound contains at least one asymmetric carbon, then we call that as chiral compound. It's also, asymmetric center is also called as stereo center. So that's about chiral compound. Next one is enantiomers. What are enantiomers? These are non-superimposable mirror images. Non-superimposable mirror images are called enantiomers. See, if they are like this, my hands, mirror image. If I keep one hand, another hand like this, it looks like mirror image of this, but I cannot superimpose this on this one. In the same way, there will be certain compounds. I'll write one example. If I take CHO, COH, HCOH, HCH2, OH. Okay, and if I take the mirror image of this, we get CHO, OH on this side, HH on this side. One is mirror image of the another, but if I start keeping one over the another, then this OH will overlap with this hydrogen. So I cannot impose this. This type of non-superimposable mirror images are called enantiomers. Next one we have is diastereomers. Diastereomers are non-mirror images. They will be having same molecular formula, but they are non-mirror images. For example, take this CHO, CH2OH. In this example, CHO, both of them have same molecular formula, but I cannot superimpose on one another. Are they mirror images? No, they are non-mirror images. See, OH is this side OH should come, but I have hydrogen here. These type of non-mirror images are called diastereomers, but their molecular formula will be same. So these are some important terms which you should know. Next one is elimination reaction. This is also called as beta elimination reaction. In elimination reaction, what happens? What will be there in elimination reaction? See, alkyl halide will be there. When alkyl halides, CH3, CH3, any halogen, when they are treated with alcoholic KOH, remember, with aqueous KOH, nucleophilic substitution reaction takes place. With alcoholic KOH, beta elimination takes place. That means, see, halogen will be eliminated. This carbon is halogen containing carbon is called alpha carbon atom, and other two beta carbon atoms are there. So from beta carbon atom, hydrogen will be eliminated. So what we get? We get alkene, CH3, CH, double bond, CH2. So one hydrogen H2O and KCl will be removed. These type of reactions are called beta elimination reaction. Beta elimination reaction takes place in the presence of important. Remember this reagent important when alcoholic KOH. With aqueous KOH, what do we get? We get nucleophilic substitution reaction. Next reaction we have is reaction with metals. In case of reaction with metals, what will be there? Alkyl halide RX will react with magnesium. First, let me consider of magnesium in the presence of dry ether. Dry ether. So, what do we get here with dry ether? 1 minute. Okay. With the dry ether, we get alkyl magnesium halide. This alkyl magnesium halide is called Grignard reagent. Grignard reagent. So alkyl magnesium halide is called Grignard reagent. Remember this. This is how alkyl halide reacts with magnesium. And one of the important reaction here we have is Wood's reaction. When alkyl halide react with sodium, I'll take two molecules of alkyl halide. This one NaX will be removed. 2 NaX will be removed and we get, along with this, we get higher alkane. This reaction is called Wood's reaction. This reaction is called Wood's reaction. So that's about reaction of haloalkanes with metals. Next we have reaction of haloarenes. Yeah, reaction of haloarenes here. First reaction we have is nucleophilic substitution reaction. In nucleophilic, see, alkyl halide, it's very in case of alkyl halides, it's very easy to do nucleophilic substitution reaction. But in case of aryl halide, it's difficult to do nucleophilic substitution reaction. That is because of resonance, carbon and halogen. See, I'll show you. In case of aryl halide, halogen is attached to first thing sp2 hybrid carbon atom. It's difficult to break the bond. sp2 hybrid carbon atom is electron withdrawing group. It will not leave chlorine. That's one thing. And second thing is benzene ring is already electron rich. So nucleophile is also rich in electron. So repulsion will be there between nucleophile and benzene ring. That is the second reason. And because of resonance, this carbon and halogen bond acquires double bond character. Because of that, it's difficult to break the bond. That's why in case of aryl halides, it's not very easy to perform nucleophilic substitution reaction. Either we require very high temperature like this reacts with chlorobenzene, reacts with NaOH, which requires 623 Kelvin temperature as well as 300 atmospheric pressure, followed by treatment with H plus ion. Acidification, it forms OH. Okay, OH group will be substituted. In case of alkyl halide, it was very easy. But in case of aryl halide, it is difficult because of the reasons which I have told you. So that's why we take either very high temperature and pressure, or if I attach electron withdrawing groups like this, I'll take 3 electron withdrawing groups, NO2, NO2, NO2 like this. If I attach 3 electron withdrawing group on just warming with water, then nucleophilic substitution reaction takes place. OH group will be attached. That here it's taking place because on just warming, that's because of the presence of 3 electron withdrawing groups over there. So that's about nucleophilic substitution reaction. And when I come to reaction with metals, see, we have learned reaction of haloalkanes with metals. That is Wood's reaction. One reaction was Wood's reaction, that two molecules of alkyl halide reacted with sodium in the presence of dry ether. In case, first I'll start with Fittig reaction. aryl halides. Two molecules of aryl halides will be there when they react with sodium in the presence of dry ether. Here biphenyl will be formed. What product formation takes place? Biphenyl formation takes place with the liberation of like byproduct NaX will be eliminated. So this reaction is called Fittig reaction. Fittig reaction is for aryl halides. Woods reaction is for alkyl halides. In both the case we used dry ether. Dry ether. Next we have is Woods-Fittig reaction. It's a combination of Woods reaction and Fittig reaction. That means one alkyl halide will be there and another one aryl halide will be there. Alkyl halide with sodium and one more is aryl halide. This is a combination of Woods reaction and Fittig reaction. See, this will be removed and alkyl benzene formation takes place. Alkyl group will be attached to benzene ring. So this reaction is called Woods-Fittig reaction. And last one is electrophilic substitution reaction. See, electrophilic substitution reaction in benzene ring is very simple one. This chlorobenzene, or if you take any halogen substituted benzene, they acts as ortho and para directing group. Your nitration, halogenation, Friedel-Crafts alkylation, Friedel-Crafts acylation, all these in all these electrophilic substitution reaction, substitution takes place at which place? Ortho and para places, and para being the major. I'll give only one example. Friedel-Crafts alkylation, when chlorobenzene is treated with alkyl halide CH3Cl in the presence of anhydrous AlCl3, we get ortho and para substituted, ortho substituted product and one more para substituted, so CH3, one more para substituted product. So here para being the major. In all electrophilic substitution reaction, para product will be formed as a major product. Remember this. In all electrophilic substitution reaction, it's same. So that's about reactions of haloalkanes and haloarenes. That completes the chapter haloalkane and haloarene. So next chapter we have is alcohols, phenols and ethers. Next chapter. Here we are studying only important reaction. Next chapter. Alcohols, phenols and ethers. See, if you have any doubt in any of the topic in haloalkanes and haloarenes, leave a comment in comment section. I'll answer those questions. Now let's start with alcohols. First, let's complete reactions, properties of alcohol. What is the general formula of alcohol? ROH. ROH is the general formula of alcohol. If I start with the classification of alcohol, alcohols are classified into primary, secondary and monohydric, dihydric will be there, like haloalkanes and haloarenes. Monohydric means only one OH group will be there. I'll write it quickly. Monohydric, dihydric, polyhydric alcohols will be there. So monohydric is further classified into again primary alcohol, secondary alcohol and tertiary alcohol. Primary alcohol, OH group is attached to primary carbon. Secondary alcohol, OH group is attached to secondary carbon, and another one is OH group attached to tertiary carbon. And if OH group is directly attached to CH2OH, so this type of alcohol, like OH group is directly attached to sp2 hybrid carbon atom, then that's called allylic alcohol. Allylic alcohol. OH group will be attached to sp2 hybrid carbon atom. So we have studied allylic halide, right? In the same way, this is also. And if it is OH group is attached to CH2, that is sp3 hybrid carbon, which is attached to benzene ring, then this is called benzylic alcohol. Benzylic alcohol. If you study the classification in haloalkanes and haloarenes, it's almost same classification. Next, primary, secondary, tertiary is over. Allylic alcohol and benzylic alcohols are over. So dihydric, trihydric, polyhydric will come. Many OH group will be there. So these are certain classification of alcohol. Next, if I come to structure of alcohol, R O H. Here the bond angle between R and H is 108.9 degree. Okay, 108.9 degree. And what is the hybridization of carbon? Carbon hybridization is sp3 and oxygen hybridization is also sp3. Oxygen undergoes sp3 hybridization here. And if you consider preparation of alcohol, how can we prepare alcohol? What are the different methods of preparation? First method of preparation of alcohol is preparation. First method of preparation is from alkyl halide. Alkyl halide. How can we prepare alcohol from alkyl halide? Nucleophilic substitution reaction of alkyl halides. Alkyl halide reacts with aqueous KOH to form ROH. This is one method of preparation by treating them with aqueous KOH. We have one more reagent which reacts with alkyl halide to form alcohol, that is moist silver hydroxide, or you can take aqueous K2CO3. Both of them form ROH. So alkyl halides can be converted into ROH by using three different reagents. One is aqueous KOH, another one is moist AgOH, or you can take aqueous K2CO3, that is potassium carbonate. Aqueous potassium carbonate also forms ROH. So this is the method of preparation from alkyl halide. And second method of preparation is from alkene. From alkene. See, from alkene we have to form alcohol. I'll take general example of alkene. C double bond C will be that. Here there are different, from here to I should form C and OH. Other groups will be there. Like this. Here to here I have to go. Here also we have three different reagents. I'll mention the reagents one by one. All of them will convert alkene to alcohol only. Remember, first one, if you treat it with concentrated, first reagent you can use is forming this one, concentrated H2SO4 in the presence of water, H2O. Okay, so this is acid hydrolysis of alkene to form alcohol. Acid hydrolysis of alkene, addition takes place according to Markovnikov's rule. It's just addition of water to alkene. Addition takes place according to Markovnikov's rule. Here we require which one? Acid as catalyst. That is one method, and another one is, 1 minute. Okay, another one is we can treat this one with B2H6. B2H6 in the presence of tetrahydrofuran. Tetrahydrofuran, and this is followed by treatment with H2O2 hydrogen peroxide in the presence of OH minus. So this is one way of synthesizing. This is another way of synthesizing, and we have one more way of synthesizing, that is on treatment with mercuric acetate, HgOAc twice in the presence of tetrahydrofuran, and followed by treatment with NaPH4, sodium borohydride, in the presence of base. This also produces or converts alkene into alcohol. So see, in above also we have three different reagent. Here also remember we have three different reagent. All these reagents convert alkene into alcohol. Next method of preparation is from carbonyl compounds. From carbonyl compounds. What are carbonyl compounds? Carbonyl, we are going to learn that in next chapter again. Carbonyl compounds are aldehyde ketones. All these are called carbonyl compounds. How carbonyl compounds produces? Carbonyl compounds on reduction, aldehyde and ketones on reduction produces alcohol. First, let me take one example of aldehyde, general example of aldehyde, RCHO. This on reduction with hydrogen in the presence of platinum, palladium or nickel. Reduction should be that. Reduction of this one in the aldehyde in the presence of all platinum, palladium or nickel produces RCH2OH, that is primary alcohol. Remember, aldehydes produces primary alcohol. If in case of, instead of aldehyde, if I take ketone, R C double bond O R, this on reduction, let me take sodium borohydride NaBH4, or you can use lithium aluminium hydride, or you can use sodium in the presence of ethanol. In the presence of ethanol, all these three can be used as reducing agent, which converts our yeah, sorry for the inconvenience. We got some technical errors. Fine. Let me continue. Okay. So now we got completed till reduction of reduction preparation of alcohol by reduction of carboxylic acid. Here also we get primary alcohol. Next we have is physical properties of alcohol. Physical properties. These alcohols are colorless liquid with characteristic smell. They will be having their own smell. And if I go to higher alcohols, they are colorless as well as odorless in nature. And are they soluble in water? Yes, because since they form hydrogen bond, they are soluble in water. And as the solubility decreases with increased number of carbon atoms, because they are hydrophobic in nature, and their boiling point will be high because of formation of hydrogen bonding in them. So these are physical properties of alcohol. Next, if I come to chemical properties, here we come across two different types of reactions. First one is reaction involving breakage of C. We have like this: ROH. Some reaction involve breakage of carbon and oxygen bond. Some reaction involves breakage of oxygen and hydrogen bond. First, let us start discussing, or let's discuss about the reaction which involves breakage of reaction reaction involving OH bond cleavage. OH bond cleavage. Okay, OH bond will break in those type of reaction we are going to study first. Later let's discuss about carbon and oxygen bond cleavage reaction. Among them, first see, when these alcohol ROH react with metals, that may be either sodium or potassium, or it can be aluminium also. It reacts with aluminium also. It produces RONA with liberation of H2. Remember this: alcohol on reaction with sodium produces which gas? Hydrogen gas. Hydrogen gas will be liberated. Or in case if I treat it with aluminium, it forms RO 3 times aluminium with the liberation of H2. Okay, so remember this reaction. And if I treat alcohol with metallic hydrides, sodium hydride, potassium hydride, like that, metallic hydrides, it forms ROM along with liberation of H2. Metallic hydride also liberate hydrogen gas from alcohol. Next, if I treat alcohol with NaNH2, here also again OH bond will break. Na will be substituted in the presence of in the place of hydrogen. We get RONA plus NH3. NH3 gas will be liberated. And when I treat it with, this is one very important reaction, when we treat it with RCOOH in the presence of H plus, this react forms ROC double bond O R with H2O. This reaction is called esterification reaction. When OH, that's alcohol reacts with acid in the presence of alcohol react with carboxylic acid in the presence of acid, it produces ester. This reaction is called esterification reaction. Or it can also react with azyl chloride, RC double bond O Cl, in the presence of pyridine. In the presence of pyridine, again same product will be formed, COR, that is ester formation takes place, byproduct will be different. Or acid anhydride also produces ester only, RCO twice O in the presence of H plus. That is, when alcohol react with acid, acid chloride or acid anhydride, they produces ester. All these reaction involve cleavage of OH bond. Remember, produce and RCOOH will be byproduct. So these three reactions are called esterification reaction. Esterification reaction. Okay, so next is reaction with Grignard reagent. ROH reacts with Grignard reagent RMgX to form ROMgX. MgX will be substituted there along with formation of alkane. We get alkane. When alcohol react with alkyl magnesium halide, that's Grignard reagent, we get alkane. And next reaction with concentrated sulfuric acid, concentrated H2SO4, they form ROSO2OH. This is not that much important reaction. H2O with concentrated HNO3, RONO2 will be substituted. So this is not very much important. Take only this reaction if you want. This is just for your information. So this is how these are different reaction where breakage of OH bond will takes place in case of alcohol. Next we have is reactions involving cleavage of CO bond. Reaction involving cleavage of CO bond. Here also we have many reactions. Let us study the reactions one by one. First, ROH is the starting material in all the case. So let's start writing the different reagents now and the reaction, how the reaction takes place. First, alcohol reacts with anhydrous zinc chloride in the presence of HCl. Which reaction? What is the name of the reagent? Anhydrous ZnCl2. Lucas reagent, it forms Rx plus H2O. Okay, we have studied this reaction already. It reacts with PCl3 to form RCl along with H3PO3. It reacts with PCl5 to produce RCl, HCl and POCl3. I'm not going to write all the products here because this one we have already discussed. So they react with red phosphorus in the presence of halogen to produce alkyl halides, and the reaction with SOCl2 to produce alkyl halide. All these reactions are over. SOCl2. I'm not going to revise that again. So, and one more important reaction is when alcohols are treated with concentrated sulfuric acid. Alcohol reacts with concentrated sulfuric acid. On heating with concentrated sulfuric acid is a dehydrating agent. It removes water molecule that leads to formation of double bond. Instead of concentrated sulfuric acid, you can also use H3PO4. Concentrated or concentrated H3PO4 can also be used, which is also a dehydrating agent. So important one. Next we have is if I do oxidation. If we do oxidation of alcohol, which produces aldehyde RCHO, which on further oxidation produces acid RCOOH. When I treat alcohol with acidic or basic KMNO4, KMNO4 is a strong oxidizing agent. KMNO4 in the presence of H plus or OH minus produces RCOOH. This is a strong oxidizing agent which directly oxidizes alcohol into carboxylic acid. And if I treat it with mild oxidizing agents like PCC, pyridinium chlorochromate, which is a mild oxidizing agent, I'll not directly get acid, we get aldehyde RCHO. Remember, with KMNO4 and K2Cr2O7, which are strong oxidizing agent, we get alcohol directly converted into acid. Whereas if I want to stop the reaction at aldehyde or ketone, we have to use mild oxidizing agent like PCC. And when alcohols are treated with copper at 573 Kelvin temperature, we get RCHO. This is from primary alcohol. If the alcohol is primary, we get aldehyde. If the alcohol is secondary, we get ketone RCOR. And if we have tertiary alcohol, then what we get? We get alkene. Okay, so with alcohol with copper at 573 Kelvin temperature, primary alcohol produces aldehyde, secondary alcohols produces ketone, whereas tertiary alcohol produces alkene. So these are some reactions of alcohol, and these are important things about alcohol. Next we have is Lucas test. We have already discussed in first chapter. Next, phenols. Phenols is very simple because you have studied almost all kind of electrophilic substitution reactions and all in phenol. The only thing is you need to learn the preparation of phenol. Next one is phenols. Phenols means OH group will be attached to benzene ring. If OH group is attached to benzene ring, then we call that as phenol. OH group attached to benzene ring is called phenol. If I take the preparation of phenol, then from first method of preparation is from benzene sulfonic acid, benzene sulfonic acid. So what is the formula of benzene sulfonic acid? Benzene attached to SO3H. This is benzene sulfonic acid. Benzene sulfonic acid on treatment with NaOH followed by acidification. Produces phenol. OH. This is method of preparation of phenol from benzene sulfonic acid. first hydrogen will be replaced by sodium, and then again we perform this, then ONA, that SO3 Na group will be substituted by ONA. Instead of following all those things, you just remember this, that's enough. And next is from diazonium salt. I told you diazonium salts are very unstable. So if we just warm benzene diazonium salt, N2 plus Cl minus, just on warming produces phenol, OH. Okay, this is from benzene diazonium salt. And if I take this one, phenyl magnesium bromide, phenyl magnesium bromide, and this one on treatment with oxygen in the presence of dry ether produces OMgBr. This on further acid hydrolysis produces phenol. Phenol is produced. Okay, so remember this. And next one, important one, is from which one? Let's take yeah, next is from haloarenes. Like if I take chlorobenzene, this is important process from chlorobenzene. Take chlorine, and when you treat chlorine with sodium hydroxide, NaOH, at higher temperature, it forms ONA. 300 atmospheric pressure is required here. This on further hydrolysis, when you treat it acidification with dilute acid, produces phenol. This method is called Dow's process. This method of preparation is called Dow's process. Is it clear? So we have studied that this is nucleophilic substitution reaction of aryl halide, which is very difficult. That's why it requires higher pressure. Next one is from cumin. What is the formula of cumin? CH, CH3, CH3. Cumin on oxidation followed by acidification, acid hydrolysis, produces phenol. Cumin hydroperoxide will be obtained, that produces further acidification, produces phenol. These are different methods of preparation of phenol. See, phenols are also colorless and these are crystalline solids. They will be having their characteristic odor, that's called phenolic odor will be there. And if I consider their boiling point, that boiling point will be usually higher than corresponding aromatic hydrocarbon. That's because of formation of yes, Ajay Vishnu. Okay, that gives phenol. Yes, that's right. Okay, we are talking about physical properties of phenol. Okay, they will be having higher boiling point because of formation of hydrogen bonding, whereas normal aromatic hydrocarbon will not form hydrogen bonding. See, these are lower members, like phenols are soluble in water, they because they form hydrogen bonding. This is physical property. And if I start with chemical properties of all phenols, first test we have is detection test. This is very important, concentrate on this one. First test we have is ferric chloride test. That's also called neutral ferric chloride. You have done this in lab actually. Here, phenols react with OH react with FeCl3 to form H plus ions will be liberated. Along with that, it forms a complex FeOC6H5 6 times minus 3 plus HCl. This is a violet color complex. This is a violet color complex, important one. Remember this formula. Okay, neutral ferric chloride, violet color formation takes place because of formation of this complex. Remember this. So this is test for detection of phenol. And another test we have is bromine water test. Bromine water test. So if I treat phenol with bromine water, it produces white color precipitate. Why it produces white color precipitate? Do you know? I'll write the reaction. That white color precipitate is because of tribromo substituted product OH phenol on treatment with bromine water Br2 H2O produces OH Br Br Br. This is white color precipitate. White color precipitate. This is also used in the detection of phenol. Remember, on treatment with bromine water, phenols produces white color precipitate. So next is different chemical reactions which involves phenol. Let us study chemical reactions one by one in phenol. The above two which we have discussed were test for phenol. Important one, remember. Now, when phenols okay, when these phenols react with zinc dust, when I heat phenol with zinc dust, what do we get? We get benzene. Okay, direct benzene is obtained on reaction on heating with zinc dust. And if I heat this one with Br2, or if I treat phenol with Br2, tribromo product will be formed. Just we have discussed this one, Br, Br, and Br will be substituted, which is a white color precipitate. And if I treat phenol with Br2 in the presence of CS2, carbon disulfide. Above we have used water, aqueous, but here non-aqueous solvents like carbon disulfide. Either we get ortho and para product. Orthobromophenol and parabromophenol. Para being the major product. And in the same way, all electrophilic substitution reactions takes place with dilute HNO3. NO2 group will be substituted to ortho and para positions with and one more thing, with concentrated HNO3 the reaction is different. I'm not going to write the product for dilute HNO3. Orthonitrophenol and paranitrophenol formation takes place with concentrated HNO3 and H2 concentrated H2SO4. If we treat phenol, we get picric acid. NO2, NO2, NO2. So this is what happens. All these are electrophilic substitution reaction, and if I treat it with CH3 Cl in the presence of anhydrous AlCl3, CH3 group will be substituted to ortho and para position, and if we treat that one with azyl chloride in the presence of AlCl3, then azyl substituted product will be formed. All these are electrophilic substitution reactions. And if I treat phenol with sodium or sodium hydroxide, we get sodium phenoxide. O Na will be substituted. And if I treat phenol with Na2Cr2O7, sodium dichromate in the presence of H2SO4, we get quinone. Oxidized product, quinone will be formed. And see, we have two important reactions here. I'm going to write them here. First, if I treat phenol with hydrogen in the presence of nickel at 533 Kelvin temperature, we get, or like all double bond will be removed, cyclohexanol will be produced. And now let's come to coal base reaction. Coal base reaction. See, phenols on treatment with sodium hydroxide NaOH produces sodium phenoxide Na will be produced. This on further treatment with carbon dioxide at 4 to 7 atmospheric pressure and 400 Kelvin temperature, followed by acidification, we get salicylic acid, COOH. Salicylic acid will be formed. This reaction is called coal base reaction. Okay, and we have one more reaction, that is Reimer-Tiemann reaction. Reimer-Tiemann reaction. In the Reimer-Tiemann reaction, phenol is treated with CHCl3 in the presence of NaOH. Here we are not going to write intermediates and all. You should know the product, that is the main thing. CHO. This is for on further acid hydrolysis produces salicyl aldehyde, OH and CHO. So if it produces salicylic acid, then that is in coal base reaction. Salicyl aldehyde is Reimer-Tiemann reaction. Remember, these two are important reactions. These are few reactions about phenols, reactions of phenol. Next we have is ether. Ethers. So what is the general formula of ether? Ethers are represented by R, O, R dash. R and R dash can be same or they can be different. If they are same, then they come under the category symmetrical ethers. If they are different, then they come under the category mixed ethers. Okay. If I consider the structure of ether, here oxygen undergoes sp3 hybridization, but the bond angle is 111.7 degree because of lone pair bond pair repulsion. The bond angle changes, we know that. And how can we prepare ethers? What is the method of preparation of ether? First one is from alcohols. Alcohols on dehydration. If I treat two molecules of alcohol, ROH, on treatment with H2SO4 at 413 Kelvin temperature. Remember the temperature. Alcohols on treatment with H2SO4 at 413 Kelvin temperature produces ethers. And if you take alkyl halide, they react with sodium alkoxide RONA to form ether. This reaction is called Williamson ether synthesis. This reaction, what is the name given to this? Williamson ether synthesis. Okay, see, in Williamson ether synthesis, can we use secondary and tertiary alkyl groups? Can we see the Can we use secondary and tertiary alkyl groups in Williamson's ether synthesis? Yes. Second, if I take secondary and tertiary alkyl groups, they take which mechanism? SN2 mechanism. This is nucleophilic substitution reaction of haloalkanes. We have studied the same reaction, nucleophilic substitution. If I take secondary and tertiary alkyl groups, here, alkyl halides, if they are secondary and tertiary, they follow SN2 mechanism. Remember this. And if I take reactions of ether, R, O, R, when they react with hydrogen halide, what they produce? Break the bond, ROH, one alcohol will be produced, another one alkyl halides will be produced. And when I treat aromatic ether, OR, with hydrogen iodide, it forms phenol. OH. Always whenever benzene ring is there, phenol formation takes place, not iodobenzene. Remember this reaction. Plus R I. And if I have tertiary group on one side, CH3, 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 like this. One is tertiary group, another one is primary group. And when I treat this one with hydrogen iodide, so on which side hydrogen will be attached and which compound halogen will be attached? This halogen will attach to tertiary carbon. I plus CH3 OH, methanol formation takes place. So this is a thing. And if I consider any electrophilic substitution reaction, electrophilic substitution reactions of ethers takes place at ortho and para positions. So remember this one, they are ortho para directing group, they are electron donating group. Electron donating group always directs the incoming electrophile to ortho and para position. That completes alcohols, phenols and ether chapter. Next we have is aldehyde ketones and carboxylic acid, that we are going to let's take a 10 minutes break before that and let's continue further. Okay, so it's 12:54 now. We'll be back at 1:05. Yes, we are back on time. Okay, now let's start with next chapter, that is aldehyde, ketones and carboxylic acid. Aldehyde, ketones and carboxylic acid. See, in this one we have so many reactions in this one as well as the next chapter. Next chapter is simple amines. So I'll in aldehyde and ketones, I'll directly start with preparation of aldehyde and ketone. We're not going in very much deep into introduction things and all, and physical properties, all those things we are not going to study because it takes very much time. That all those things we are going to discuss in normal classes, normal lengthier classes. I'll explain everything in detail. So here, since it is just brushing up your memory, let's go with the reactions first. First one we have is, we are starting with aldehydes. Aldehydes, ketones and carboxylic acid. Aldehyde, ketones and carboxylic acid. First one is preparation of aldehyde and ketone. Later let's study about carboxylic acid. First let me complete aldehyde and ketone because their chemistry is almost similar. Only one group difference is there in aldehyde and ketone. That's why they will give almost similar kinds of reactions. That's why we are going to study them in detail. Preparation, we are going to study them together. Preparation of aldehyde and ketone. Preparation of aldehydes and ketone. First one, if I take alcohol, first method of preparation is from oxidation of alcohol. Oxidation of alcohol. If I take alcohol and primary alcohols, we have discussed this reaction. Primary alcohols on oxidation produces aldehyde, and if I take secondary alcohol, they produce ketone. Okay, so that's one thing. And one more is that here we use any oxidizing agent, and if I use copper also, primary alcohols are CH2OH, on heating with copper at 573 Kelvin temperature produces aldehyde RCHO with liberation of hydrogen gas. And if I consider secondary alcohol, RCRHOH, this on treatment with copper at 573 Kelvin temperature produces ketone, C double bond OC with the liberation of hydrogen gas. Remember this. And next is from alkene, next method of preparation. This one we are not going very much deep because in previous chapter we have discussed this question, reaction. If I consider alkene, RCH double bond CHR, and on treatment with ozone O3, what happens? In the presence of either you can take CHCl3 or you can take CCl4, carbon tetrachloride also you can take, they produce one intermediate RCHC. In the place here in between CH and CH we have double bond, right? That double between those double bonds, the oxygen need to. Then this on further treatment with zinc and water, the bond will break like this. The bond will break like this, and another bond will break like this, and what we get is RCHO plus ZN. Okay, so this reaction is one of the very important reaction where alkenes are converted into aldehyde on reaction with ozone. Next we have is Rosenmund reduction. Next, Rosenmund reduction. What happens in Rosenmund reduction? Azyl chloride will be there. This is one of the way to convert azyl chlorides into aldehydes. Azyl chlorides RCOCl are treated with or reduced in the presence of hydrogen supported over palladium, in the presence of palladium supported over barium sulfate. Reduction of azyl chloride with hydrogen in the presence of catalyst palladium supported over barium sulfate produces aldehyde RCHO. This reaction is called Rosenmund reduction. HCl. And from nitriles also we can prepare aldehydes. So how can we prepare aldehydes from nitrile? There are different reagents. Nitriles also on reduction produces aldehydes. What is the formula of nitrile? R C triple bond N. When nitriles are treated with what is the name of this reagent? What is I refers to here? Comment in the comment section. Tertiary butyl aluminium hydride. Okay, so followed by H2O produces RCHO. Okay, so this is one reagent, and another one reagent is I can use RMgX in the presence of dry ether. This followed by acid hydrolysis H3O plus. This produces RCO. Ketone will be produced. C with tertiary butyl aluminium hydride, what we are getting is aldehyde with alkyl magnesium bromide. That's with Grignard reagent we are getting ketone. And if I treat them in the presence of SnCl2 with HCl followed by in the presence of ether and water, ether, next is hydrolysis produces RCHO. This reaction is called Stefan's reaction. Stefan's reaction or Stefan's reduction. Remember Rosenmund reduction and Stefan's reduction. Both are important ones. Next reaction we have is Gattermann-Koch reaction. 1 minute. Okay, now let's continue further. Next is Gatterman-Koch reaction. Gatterman-Koch reaction. Okay. Oh, sorry. This is Al. This is commonly known as Debal H actually. Debal H diisobutyl aluminium hydride. I think I told tertiary butyl, sorry. That's diisobutyl aluminium hydride. Okay, Gatterman-Koch reaction. Next one is Gatterman-Koch reaction. In Gatterman-Koch reaction, what we do is we take benzene. Benzene is treated with carbon monoxide in the presence of HCl, and we require anhydrous AlCl3 and CuCl. Gatterman reaction was different. Gatterman-Koch reaction is different. This produces aldehyde. CHO group will be substituted. This is one method from Gatterman-Koch reaction. And next one is, if I do Friedel-Crafts acylation of benzene. Take benzene. Benzene ring. Friedel-Crafts acylation. What we use RC double bond OCl in the presence of anhydrous AlCl3. Here RCO group will be substituted to benzene ring and we get aromatic ketone. C double bond O R will be obtained. This is another method from benzene. This reaction is called Friedel-Crafts acylation. We already know this. Next is from alkyne. Also we can prepare aldehydes as well as ketones also. If I take alkynes, and when alkynes are treated with dilute sulfuric acid, dilute H2SO4 in the presence of HgSO4 at 333 Kelvin temperature. Alkynes on treatment with dilute sulfuric acid in the presence of HgSO4 at 133 Kelvin temperature, they produce RCHO or RCOR. That depends on the group which you are taking. Other group here and here groups will be there, right? That depends on that one. Either you will get aldehyde or you will get ketone. Or you can use one more reagent here, is diborane, B2H6 in the presence of tetrahydrofuran, followed by treatment with hydrogen peroxide in the presence of base. This also produces either aldehyde or ketone. For conversion of alkyne into carbonyl compounds, we have two different reagents. One is dilute sulfuric acid in the presence of HgSO4, and next one is B2H6 in the presence of tetrahydrofuran, followed by peroxide in the presence of base. Okay, so this is the thing. And next one is, see, this one. If we treat CH3 with, first is CrO2Cl2 and second followed by acid hydrolysis, what do we get? Alkyl benzene on treatment with CrO2Cl2 followed by acid hydrolysis, we get aldehyde. And this is one of the important named reaction. Benzaldehyde is obtained. This reaction is called Itard's reaction. Itard's reaction. And yes, these are our different methods of preparation of aldehydes as well as ketones. Okay, next if we start with properties, chemical properties, that two mainly. First is the nucleophilic addition reaction. See here we have like this, C double bond O, like this, where nucleophile will attack. We have nucleophile. Mean here oxygen gets partial negative charge, carbon gets partial positive charge. So nucleophilic attack takes place on carbon, then these electrons will move on oxygen, remember. Okay, we have different nucleophilic substitution reaction which involves C double bond O, carbon. Both aldehyde as well as ketone will react in the same manner for all these with all these reagent. When I treat carbonyl compounds with alcohol ROH in the presence of dry HCl, hemiacetal formation takes place. First step, what will be formed? Hemiacetal. We have OH minus here. OH minus will go and attack to this carbon, and alkyl group will be attached to oxygen. COROH. What is this? This is hemiacetal. This hemiacetal will react with one more molecule of alcohol ROH in the presence of dry HCl, and it produces acetal. OR and OR. This is acetal. Okay, hemiacetal and acetal formation. With alcohol, aldehyde produces acetal and hemiacetals. Next, when I treat this one with CH2OH and CH2OH, dihydric alcohol, that's glycol. Write the product. Here we get a cyclic product. Oxygen, CH2O, CH2. This product will be obtained. Here also we use dry HCl. And with HCN, cyanohydrine formation takes place. What is the structure of cyanohydrine? See other two bonds as it is. One is OH, another one is CN. CN minus will go and attach, and oxygen will take that hydrogen. So the name of this compound is cyanohydrine. Cyanohydrine formation takes place. And when I treat this one with sodium bisulfite, NaHSO3, bisulfite formation takes place. We get see here NaO3 S or SNaO3 also you can write. That's 1 minute. SO3 Na, and another one is OH. Later this H and Na will change their place also. Initially with O, Na will be attached, but later they will change that place and this will be the final product. And with Grignard reagent, what will be formed with Grignard reagent? R MgX. This on further hydrolysis, acid hydrolysis, H3O plus, it produces RCOH, like this. Okay, so these are the some few reactions which are nucleophilic addition reaction takes place. And in some cases what happens, see this reaction. One minute. when these carbonyl compounds are treated with NH3 on heating, followed by form imines. Skip, see, imines are nothing but instead of nitro oxygen add double bond N. These are called imines. Imines formation takes place. Okay, so in the same way, like any group can be present like this one on treatment with, in the place of, I'll write Z can be any group. I'll write the Z group. This is general, and followed by heating. If I heat this, they form like the C double bond N. Z group will be there. So what are these Z groups? What might be in Z? Z may be any aryl group, or it can be alkyl group also, or it can be OH also, or it can be NH2 also, or it can be NHC6, H5, all these group, or it can be amide also, NHCO, NH2 also. All these groups will be attached there in the place of Z. You can write the same reaction for any of this one. Okay, next if I consider oxidation reaction of aldehyde. Aldehyde undergo oxidation in the presence of different reagent, aldehyde as well as ketone. In the presence of different reagent, the product formed will be different. Now, check one by one which are the products formed here. I'll take general example of aldehyde. R, C double bond O, R dash. We are studying oxidation reactions. Oxidation reactions of aldehyde. If I treat aldehyde with K2Cr2O7, that is potassium dichromate, K2Cr2O7, in the presence of acid. Oxidation reaction, aldehydes are oxidized into corresponding acid. RCOOH will be formed. Okay, is it clear? They will be oxidized to corresponding acids. Next, if I treat them with, this is important one, if I treat them with a complex, first take the formula, then you can write the name. AgNH3 twice plus in the presence of base OH minus. Here this reagent is called Tollens reagent. By using Tollens reagent, silver will get precipitated. Aldehyde or aldehyde will be converted into corresponding acid and precipitate formation takes place. This reaction is only for aldehyde. Only for aldehyde. This is called Tollens reagent. This reagent is called, I'll write, okay, Tollens reagent. So ammoniacal silver nitrate is called Tollens reagent. And what is the product we get? We get RCOO minus along with Ag. Silver mirror formation takes place. Ag will get precipitated. This reaction is used for detection of aldehyde. Only aldehyde will give this test, not the ketones. Next reaction is, next oxidation reaction is on these on oxidation with copper Cu plus 2 in the presence of base OH minus. This mixture is called Rockwell salt. Along with Rockwell salt, Rockel salt, we get RCOO minus. Obviously, acid formation takes place along with formation of Cu2O precipitate, which is red color precipitate. This is a red color precipitate, and this test is also given by only aldehyde. This is one of the detection tests for aldehyde. And what is the name of this test? Test is called Felling's test. Felling's test. Okay, Felling's reagent or Felling's test. So copper and Cu+2 in the presence of base and Rockel salt. That mixture, one is Felling's A, another one is Felling's B. We have to add both the mixture and we have to heat it. We get silver mirror. Not silver mirror, red color precipitate formation takes place. That's because of Cu2O formation, cuprous oxide formation, and only aldehyde will give this test. So next is one more test is that okay, this is also given by only aldehyde. You can mention it. It's also given by only aldehyde. Here we treat them aldehyde with CuO, or you can take CuOH also, copper hydroxide, CuOH twice also. Along with that, we add sodium citrate. Along with that, sodium citrate is added. See, this reagent, the mixture of all this is called Benedict's reagent. What it is called? Benedict's sodium citrate, and the reagent is called Benedict's reagent. Benedict reagent, and this test is also given by only aldehyde. What happens in Benedict's test? Again, we get red color precipitate. RCOO minus will be formed along with Cu2O, which is a red color precipitate. Both in Felling's test as well as in Benedict test, since we are using copper, we get Cu2O red color precipitate. This is one of the detection test for aldehydes. So that's about oxidation reactions of all aldehydes. Next we have is reduction reactions. Reduction reactions of aldehydes or ketones. Now, if I treat aldehyde or ketone, R C double bond O R dash, if when they are reduced in the presence of hydrogen and platinum, palladium or nickel, any of the catalyst, they will be reduced to corresponding alcohol. Or I can use lithium aluminium hydride also, or we can use sodium borohydride also, NaBH4, sodium borohydride. On reduction, they produce alcohol. If it is aldehyde, they produce primary alcohol. If it is ketone, it produces secondary alcohol. So write the formula respectively. And when I treat aldehyde or ketone with zinc amalgam in the presence of HCl, this reaction is called Clemmensen reduction. Clemmensen reduction. Reduction, that means what happens, which product will be produced? We get, in the place of double bond O, we have to add only CH2 here. That's all. 2 hydrogen atoms we have to attach. Reduction, we are adding hydrogen. In Clemmensen reduction, remember the reagent zinc amalgam in the presence of HCl. And one more reagent is there. This reagent also converts into alkane, aldehyde or ketone into corresponding alkane, that is hydrogen iodide and red phosphorus. Red phosphorus. When aldehyde or ketones are treated with hydrogen iodide in the presence of red phosphorus, here also we get alkanes. And same one more reaction, similar kind. Reagent is different. Here also alkanes are produced. We use NH2 in the presence of KOH. What is the name given to this reaction? Wolff-Kishner's reduction. Wolff-Kishner reduction. Okay, these three cases we get alkane. So these are some reduction reactions of aldehydes and ketone. And next one we have is haloform reaction. We have three important reaction. One is haloform reaction, aldol condensation reaction, and Cannizzaro reaction. Let's see all these three reactions now. Okay, first let us start with haloform reaction or haloform test. Haloform reaction. See, in halo compounds which contain these type of groups, CH3, C double bond O. This at alpha position CH3 group should be there. CH3 group should be directly attached to alpha position, and one more type of group, that is CH3 CHOH. These type of group, if they are present, then only we get haloform test. Okay, here in haloform test, first step NaOH will be there. That NaOH will react with I2 and they form sodium iodide along with NaOI plus H2O. In next step, our aldehyde or ketone, C double bond O, CH3. R group may be anything. It can be one more CH3 also, H also, but at least one CH3 group should be there attached to carbonyl group. This reacts with sodium hypohalide NaOI and it forms RCOO Na along with CHI3. CHI3, what is the name of CHI3? Iodoform. We know CHCl3 is chloroform. In the same way, CHI3 is iodoform, which forms a precipitate, and it will be yellow in color. Yellow color precipitate formation takes place along with NaOH. This reaction is called haloform reaction. If CH3 group is present attached to carbonyl group, then when you add sodium hypoiodide to it, it forms yellow color precipitate of iodoform. This is haloform reaction. Next we have is aldol condensation reaction. Aldol condensation reaction. What we learn in what is aldol condensation reaction? Here the main requirement is one alpha hydrogen should be there. What is the main requirement? The carbonyl compound should contain one alpha hydrogen. One alpha hydrogen hydrogen is compulsory. Aldehydes or ketones containing one alpha hydrogen. Let me take general example and explain. Are CH2, C double bond O, H. Here, this is alpha carbon atom. On alpha carbon atom, we have hydrogen. So, alpha hydrogen is present in this case. This reacts with dilute NaOH. Dilute NaOH or dilute KOH also you can take. The compound aldehyde or ketone containing alpha hydrogen reacts in the presence of dilute alkali to produce RCH2COH on that. RCH2 CH OH CH R C double bond O H. Okay, so this product will be formed. Here, what you can see, this is alpha carbon and this one is beta carbon. On beta carbon, we have OH group. So, aldehyde or ketone containing alpha hydrogen when reacts with dilute alkali forms beta hydroxy aldehyde or beta hydroxy ketone. In beta position, OH group will be present. So, this reaction is called aldol reaction, aldol formation reaction. Aldol, alcohol as well as aldehyde will be present in this one. And this on further heating loses water molecule to form alpha beta unsaturated compound. RCH2 CH double bond CH R C double bond O H. Okay, and alpha and beta position unsaturation will be formed. Alpha beta unsaturated aldehyde will be produced. So this reaction is called aldol condensation reaction. What is the requirement for aldol condensation reaction? It should contain one alpha hydrogen. So yes, this is not one directly proportional to hydrogen. That is symbol for alpha. In alpha position, one hydrogen should be there. More than one hydrogen can be present, but one hydrogen is compulsory. This type of reaction is aldol condensation reaction. Next we have is Cannizzarose reaction. Cannizzarose reaction. In Cannizzarose reaction, we have a condition that there should not be any alpha hydrogen atom. No alpha hydrogen. No alpha hydrogen should be there. Like if you take formaldehyde, two molecules of formaldehyde react with concentrated alkali. In aldol condensation, dilute alkali was that. In Cannizzarose reaction, we have concentrated alkali. One molecule will undergo oxidation, another molecule will undergo reduction. We have HCHO, two molecules which do not contain CHO alpha hydrogen. They are reacting in the presence of concentrated alkali, KOH or NaOH you can take. They form CH3. One will form CH3OH. One will get reduced and another one will form HCO. Okay, salt of carboxylic acid will be formed. This reaction is called Cannizzarose reaction. If it occurs between two different aldehydes, then it is called cross Cannizzarose reaction. Like one you can take is benzaldehyde, another one formaldehyde you can take. These two forms cross aldol product. Sorry, not aldol, cross Cannizzarose reaction occurs. So, and this is about different reactions. And finally, let me discuss few tests for aldehydes and ketones, whether they give test or not. This is also important one. See, I'll start writing the test. test, and aldehyde and ketone. Test aldehyde and ketone. You should tell me whether they give this test or not. First test is Skiff's test. Skiff's test. Will aldehyde will give Skiff's test? Yes. Aldehyde will give Skiff's test. They give you pink color. Pink color. And ketone, no color will be there. And next one, Felling's test. Yes, I'll come to Tollens test also. Next one is Felling's test. Felling's test. What happens to aldehydes in Felling test? They give red color precipitate, and ketone, there will be no red color precipitate. And if I consider Tollens test, silver mirror will be formed in aldehyde, and there will be no silver mirror in case of ketone. Yes, okay. And 2,4 DNP, 2,4 dinitrophenylhydrazine. What happens to aldehyde with DNP? What they give? Which color they will form? Aldehydes will form orange, yellow, or you can say a red color. Orange, yellow, or sometimes red color crystals. Okay, orange or yellow or red color crystal formation takes place. Just you can say orange, red, or orange, yellow, or red color, somewhat in between. And when I come to ketone, they also give the same test. Orange, yellow, or red color crystal formation takes place. This is 2,4 DNP test is conducted to detect the carbonyl compound, not to differentiate between aldehydes and ketones. Okay, so this is about aldehydes and ketones. So we have these tests are important: Skiff's test, Felling test, and earlier we have studied many different reactions also. Learn all those reactions. Now let's go to carboxylic acid. Carboxylic acid. So you have used 2,4 DNP for the detection of aldehyde ketones in labs also. In lab, in organic test analysis, organic group analysis, same thing will be used for detection. Okay, next is preparation of carboxylic acid. Carboxylic acid, how can we prepare carboxylic acid? Let's study different methods one by one. First one is alcohol on oxidation. You can take strong oxidizing agents like KMnO4, K2Cr2O7. Alcohols on strong oxidation produces RCOOH acid. This is one thing. And aldehydes also. I'm not going to write all the reagents since we have discussed this. This one, aldehydes also on oxidation in the presence of, like we have studied Felling's reagent, Tollens, Felling test, Tollens test. All those reagents will help to convert aldehyde into carboxylic acid. As well as you can use potassium dichromate also in the presence of acid. They produce RCOOH. And if you take RCN, okay, alkyl cyanides. This alkyl cyanides on hydrolysis, alkyl cyanides on hydrolysis in the presence of HCl or H2SO4 produces RCOOH. Okay, in the presence of base, in the presence of base, they produce RCOONA. Sodium salt of carboxylic acid will be formed in the presence of base, which on further acidification produces acid, RCOOH. Salt will be converted into corresponding acid. And if you treat Grignard reagent, what is the formula of Grignard reagent? RMgX. This Grignard reagent also on treatment with CO2 in the presence of dry ether. We have to use dry ice. CO2 means not normal gas. Dry ice in the presence of dry ether produces RCOOH, carboxylic acid. And if you take alkyl amines also, amides. If you take amides also on acidification produces RCOOH. Here quite high temperature is required. You need to heat this. Okay, RCO amides on reaction with, on acidification, on just heating in the presence of acid produces carboxylic acid. Next, if you take acyl chloride, RCOCl, this one on hydrolysis followed by reaction with base or acid, H plus or OH minus produces RCOCl. So this is another method. And if you take acid anhydride also on hydrolysis produces carboxylic acid. Esters also on acid hydrolysis or basic hydrolysis produces ester. And if you consider alkenes and alkynes and alkynes, these alkenes and alkynes on treatment with KMNO4 in the presence of base, you have to heat it followed by acid hydrolysis produces carboxylic acid. RCOOH will be produced. These are different methods of preparation. And one more is preparation of benzoic acid, is that alkyl benzene on oxidation produces carboxylic acid. Only whatever may be the length of the chain, but only one COOH group will be attached there. These are different methods of preparation. Carboxylic acid always exists as a dimer. And if you take carboxylic acid, reactions of carboxylic acid reacts with sodium, or you can take sodium hydroxide or NaOH. They produce, and I'll write one by one because the byproduct formed will be different here. When they reacts with sodium, what they form? RCOO Na. This is the one product formed, along with which gas will be liberated? H2 gas will be liberated with the liberation of hydrogen gas. And if I treat RCOOH with sodium hydroxide, NaOH, one product will be same, RC, sodium salt of carboxylic acid. And here H2 gas will not be liberated, H2O will be formed. And if I treat the same thing with acid with Na2CO3, sodium carbonate, Na2CO3, what product, which gas will be liberated? With Na2CO3 as well as NaHCO3, product formed will be same. We get RCOO Na plus CO2 plus H2O. Okay, so yes, with NaOH, H2O will be liberated. With sodium carbonate and bicarbonate, CO2 gas will be released. Okay, so this is different And in all these cases, which bond is breaking? Bond between oxygen and hydrogen is breaking in all these three cases. Next, sometimes there might be chance that carbon and oxygen bond may also break. This bond may also cleave. Let's take few example for them. RC double bond O, OH. This on treatment with PCl3, or it can react with PCl5 also, or it can react with thionyl chloride SOCl2 also in the presence of pyridine. They all of them form RCOCl. That is acid chloride formation takes place when acids react with PCl3, PCl5 or SOCl2 in the presence of pyridine. Take this one also. In the presence of pyridine, they form acid chlorides. And next, when they react with NH3, on heating them with NH3, what product will be formed? On heating with NH3, they form amide. The formula of amide is RCONH2. Amide formation takes place with NH3 on heating with NH3. Water molecule will be removed. And when they are treated with these are treated with alcohol, ROH, in the presence of acid. We know this esterification, we have studied this in detail in esterification reaction, RCO. Let me consider this one as R dash for differentiating. RCOO, R dash will be formed. Ester formation takes place. This reaction is called esterification reaction. And if I heat that in the presence of P2O5, then anhydride, acid anhydride formation takes place. So I'll write that one also. With P2O5 heating, they form RC double bond O, O, C double bond O, R. Okay, so these are few things about reaction involving cleavage of COH bond. Next is full whole group reaction. See, one thing is important reaction is when you treat RCOOH with, yes, very good, lithium aluminium hydride. First one, lithium aluminium hydride, or in the presence of ether, or you can also take B2H6. Okay, in the presence of ether, both will take reaction will take place in the presence of ether, followed by hydrolysis, acid hydrolysis. What product will be produced? Lithium aluminium hydride is a reducing agent, so this will be reduced to RCH2O H. So it is a reduction reaction. Alcohol will be formed. Whole COOH group will be changed here. And if you treat this one acid with sodium hydroxide and calcium oxide. Sodium hydroxide and calcium oxide. This reaction is called decarboxylation reaction. We get RH along with formation of Na2CO3. So this reaction is called decarboxylation reaction. Decarboxylation with a mixture of NaOH and CaO. It's called decarboxylation. And comment me what is the mixture name for the mixture NaOH and CaO. Okay, so this is about a different reaction. And last important reaction is HVZ reaction. HVZ, that is Hell-Vallard-Zielinski reaction. Here, alpha halogen substitution takes place. For carboxylic acid at alpha position, halogen group will be substituted. Take general example RCH2COOH. When carboxylic acid reacts with halogen in the presence of red phosphorus followed by water, hydrolysis, it forms C, which is alpha position. This is alpha carbon. This is carbon containing oxygen, double bond O group, and the very next carbon is called alpha carbon. On that carbon, halogen will be substituted. We get CH, X, CO, OH. So this alpha halogen substituted acid formation is called Helvland-Zielinski reaction, HVZ reaction. So these are few reactions of carboxylic acid. And if I come to test of carboxylic acid, or if you are asked to differentiate between phenol and carboxylic acid, I'll take phenol one side, because both of them will give one common test, but the result will be different in both phenol and carboxylic acid. First test let us take is sodium hydrogen carbonate, NaHCO3. Will phenol react with NaHCO3? No, there will be no reaction. Whereas here brisk effervescence of CO2 formation takes place. Effervescence will be found, brisk effervescence. That's because of presence of liberation of CO2. That's first test, which is not given by phenol. Phenol will not give this test. And if I take ferric chloride, FeCl3, neutral ferric chloride test, what color will be given by phenol in neutral ferric chloride test? What color will be given? Phenol will give violet color. Phenol will give which color? Violet color. Whereas when I come to carboxylic acid will form buff colored precipitate. Buff colored precipitate. So this is a test to distinguish between phenol and carboxylic acid, neutral ferric chloride test, as well as sodium hydrogen carbonate test, which is given by carboxylic acid, not by phenol. That completes your chapter aldehyde ketones and carboxylic acid. Next, let's go to one of the easiest chapter, that is amines. Next is amines. Okay. Will this be last, ma'am? After amines, we are just going to glimpse of amines and biomolecules also. So it takes some time. In amines, we have don't have many reactions. Almost preparation after that, reactions are almost same in that one. It's very simple. Amines and diazonium salt. All that after that, just few things, only few things in biomolecules. So that's because in biomolecules you need to learn the things, just vitamins or proteins, all those things you should learn. That's why I'm going just through this glimpse of biomolecules after this one. Okay, let's start with amines. First thing we have is preparation of amine. Preparation of amines. The first method of preparation is by reduction of nitro compounds. Nitro compounds means which group will be that? In nitro compounds, we have NO2 group, RNO2. This nitro compounds on reduction in the presence of tin or HCl, or Fe in the presence of HCl, or hydrogen in the presence of platinum, palladium or nickel, or you can use lithium aluminium hydride also. Any of the reducing agents you can use. RNO2 on reduction, that's reduction of nitro compounds, we have to use reducing agent. Tin in the presence of HCl, iron in the presence of HCl, hydrogen in the presence of platinum, palladium or nickel catalyst, or lithium aluminium hydride. All this one produces are NH2. You can use any one of these reagents for the preparation. Next one is this alkyl. If you take alkyl halides, and when you do ammonolysis of alkyl halide, they also produce RNH2. But the thing is that here we get mixture of amines, primary, secondary and tertiary amines. This reaction is called ammonolysis. Ammonolysis, which is not a suitable method of synthesis, because since we get mixture of amines, we need to separate them again. Okay, so next one is reduction of RCN, nitriles. So which are the reducing agents that can be used here? We can use hydrogen in the presence of palladium, or lithium aluminium hydride, or we can use sodium amalgam NaHG in the presence of ethanol. All these can be used to reduce RCN group into RNH2 group. Okay, so next one is from amides. Amides also on reduction, RCONH2. These are also on reduction in the presence of lithium aluminium hydride in the presence of ether. Whenever you take lithium aluminium hydride, we take ether, or sodium in the presence of C2H5OH, ethanol. Or any one of these two you can use. They also produce RNH2. And next one important reaction is Gabriel thalamide synthesis. Here thalamide, we are not going to learn all the steps. Thalamide NH is treated first with alcoholic KOH. Second step, it is treated with alkyl halide and followed by acid or base hydrolysis, H2O. This produces RNH2. This is used for synthesis of only primary amines. Gabriel thalamide synthesis gives only primary amines. Okay. Next is Halfman bromamide degradation reaction. In Halfman bromamide degradation, this is also important, and Halfman bromamide degradation is also important one. We have amides RCO NH2. These amides are treated with Br2 in the presence of base KOH. Amides are heated with Br2 in the presence of KOH. We get RNH2. Here this is called degradation, because the product which you get contains one carbon less than the starting amine. So this is Halfman bromamide degradation reaction, and these are different methods of preparation of amines. Next, if I come to reactions of amines, chemical reactions. chemical reactions of amines. Let us study the reactions one by one. When amines are treated with HCl, when amines are treated with HCl, they produce, amines are basic in nature, they produce salt RNH3 plus and Cl minus. This on further treatment with base NaOH again produces RNH2. Okay, remember this, since they are base, RNH2 is basic in nature, it produces salt which on further treatment with NaOH produces RNH2. Okay, next we have is reaction with, let me consider HNO2. Reaction with HNO2. With HNO2, they produce alcohol. ROH formation takes place with the liberation of N2 gas. N2 gas will be liberated with HNO2, nitrous acid. Amines react with nitrous acid to form alcohol. Along with that, N2 gas will be liberated. If you treat amines with acid anhydride RCO twice O, we get RNHCO R dash along with RCOOH. So these are all few reactions. This is not very much important, but still it's better if you know these reactions. When these are treated with, this is important one. Important. When RNH2, that is amines, are treated with CHCl3 in the presence of alcoholic KOH. What is the name of this reaction? We get RNC. This reaction is called carbylamine reaction. Carbylamine reaction. This is used for detection of amines. Only primary amines will give this test, carbylamine test. Yes, video is lagging. Yeah, that's because of some technical errors. So it will be corrected. Okay. Carbylamine reaction. In carbylamine reaction, only primary amines will give this foul smelling substance. That's called isocyanide formation takes place. Because of that isocyanide formation, we get foul smell. Primary amines will give this test. When amines are heated with CHCl3 in the presence of alcoholic KOH, we get RNC. Next we have is reaction with C6H5SO2Cl. Here this is also not very much, this is important, it will come later. That's Heinsberg's reagent. I'll explain that in next, after completing the reaction, what is the use of this one. We get RNHSO2C6H5. This is soluble in NaOH. In some cases it is soluble, some cases it is insoluble. I'll make a star and keep it. I'll explain this once the reaction, all the reaction completes. When amines are treated with C6H5COCl, we get RNHCOC6H5. Okay, so this is the thing. And last reaction we have, all, as I'm telling you, these all reactions are not very much important. Here you have carbylamine reaction, important one, and Heinsberg's reagent, which I'll explain in next reaction. These three are very much important. These things are very much important. All these are just for your knowledge. RCOCl, they form RNHCO R dash or R. Here if you take R dash, you can keep R dash here. So these are all few reactions of amines. Now come to distinguish test between primary, secondary and tertiary alcohol. Here we use Heinsberg's reagent. What is the formula or name of Heinsberg's reagent? Heinsberg's reagent. C6H5SO2Cl. This is called Heinsberg's reagent. Heinsberg's reagent. This is nothing but benzene sulfonyl chloride. The name of this compound is benzene sulfonyl chloride, which is called Heinsberg's reagent. If I treat benzene sulfonyl chloride or Heinsberg's reagent with the primary amine, it forms one salt. That is, let me consider C6H5SO2. Here I'll consider any primary amine, that is R dash NH2. I'll consider any primary amines you can take. I'm taking general example. It forms NHR. This is further soluble in alkali. When I treat this one with base, it is soluble in base. It forms C6H5SO and R minus and K plus. Salt formation takes place. Because of the salt formation, it is soluble in base. But when I consider secondary amines, these secondary amines, they also form salt. There will be no hydrogen here. Instead of hydrogen, one more alkyl group will come there. Okay, they also form compound with Heinsberg's reagent. They also give positive test for Heinsberg's reagent, but they are insoluble in alkali. They will not soluble in alkali. The product will be formed, but the product formed is not soluble in alkali. Whereas when I take tertiary amines, there will be no reaction. Since tertiary amines, there is no hydrogen, they will not react with Heinsberg's reagent. Okay, so next test we have is carbylamine test. Carbylamine test. Tertiary amines will not give this test. Okay, in carbylamine test, what do we have? Carbylamine test, which type of amines will give positive test for carbylamine test? Only primary amines, aliphatic and aromatic primary amines will give this test. And next test we have is azo dye test. Azo dye test. So which compounds will give azo dye test? Only primary aromatic amines. Primary aromatic amines, they will give orange color dye. They give orange color dye. Orange color dye formation takes place in primary aromatic amines with azo dye test. So these are all different tests we have. Next, did I leave any test? No, I think. So these are all the tests which we have. Next we have is chemical reactions. See, if I have aniline, NH2, these reactions are very simple. NH2 is there. Okay, so this one reacts with concentrated, on heating with concentrated H2SO4, then SO3H group will be substituted at para position. Major product I am talking about SO3 H, that is sulfanilic acid formation takes place. When I treat aniline with NaNO2, NaNO2 and concentrated HCl at 0 to 5 degrees Celsius temperature, it forms C6H5N2 plus Cl minus. So these are all the, this is called benzene diazonium salt with NaNO2 and concentrated HCl, benzene diazonium salt formation takes place. And when you treat aniline with, you can say K2Cr2O7, K2Cr2O7 in the presence of H2SO4, H2SO4, it forms benzoquinone. This is the structure of benzoquinone. When aniline is treated with K2Cr2O7 in the presence of acid, that is sulfuric acid, benzoquinone formation takes place. Okay, next we have that is carbylamine test, CHCl3 in the presence of KOH, alcoholic KOH, remember, alcoholic KOH, what we get, C6H5NC will be formed. So these are next, we have one more. With remember, with bromine water, tribromo substitution takes place, as we have discussed earlier in previous chapter. And if you use treat it with bromine in the presence of pyridine, like that, only para bromo substitution, ortho and para being the major, and all other electrophilic substitution reactions also takes place there, and like nitration also you can write over there. Next we have is diazonium salt. Diazonium salt preparation is this one, same thing. Aniline reacts with NaNO2 and concentrated HCl at 0 to 5 degrees Celsius temperature. Diazonium salt formation takes place. And if you take the reactions of diazonium salt, reactions of diazonium salts are also very simple one. If you take general formula, Ar N2 plus and X minus. When you treat it with potassium iodide, when benzene diazonium salt is treated with potassium iodide, we get iodobenzene, iodobenzene formation takes place. And when I treat it with HbF4, we get ArN2 plus BF4 minus. This one on heating further forms ArF. Or if you treat it, this one with this salt with NaNO2 and copper, NaNO2 in the presence of copper, it forms ArNO2. On to substitute nitro group and fluorine, we have to treat benzene diazonium salt with HbF4. Okay, so if I treat benzene diazonium salt with water, if I treat it with water, we get phenol, ArOH. So, and the temperature should be greater than 5 degrees Celsius. Okay, if the temperature is greater than 5 degrees Celsius, they undergo hydrolysis to produce phenol. They are very unstable at higher temperature. And this one on further treatment with NaNO2, in the presence of Cu2O, if you heat it, it produces nitrobenzene, ArNO2. Nitrobenzene formation takes place. Next, if you treat benzene diazonium chloride with C6H6, that is benzene, in the presence of base NaOH, you have to heat it. It forms diphenyl. You can take ArC6H5. Okay, diphenyl formations, ARAR. C6H5, C6H5, diphenyl formation takes place. So this diphenyl, how can diphenyl be formed? One reaction was at this one, Fittig reaction. Another one is here, Woods fit, that is benzene diazonium salt on treatment with benzene produces biphenyl or diphenyl. Next, let's come to, you had said Sandmeyer's reaction. We'll come to Sandmeyer's reaction now. When benzene diazonium salt is treated with CuBr, or it is treated with CuBr in the presence of HBr, or CuCN in the presence of KCN, in the presence of KCN, or you can treat it with CuCl in the presence of HCl. Don't take all this, any one of this, okay? If you treat it with CuBr in the presence of HBr, we get AR, Br, like bromobenzene, or we get AR, CN, or AR, Cl. All these reactions are called Sandmeyer's reaction. Sandmeyer reaction. And when you treat benzene diazonium salt, with Cu in the presence of HCl, not cuprous chloride, cuprous halide, not like that. Only copper we are taking, copper in the presence of HCl, or if you take copper in the presence of HBr, or in copper in the presence of KCN. Here also same, different AR, Cl, AR, Br, AR, CN will be formed. This is called Gutterman reaction. Gutterman reaction. These are all few important reactions of benzene diazonium salt, and last reaction left is coupling reaction. In coupling reaction, we have benzene diazonium salt AR N2 plus X minus. This reacts with C6H5OH, that is either with phenol, or you can treat it with aniline also, C6H5NH2. Here, this with phenol, the reaction takes place in basic medium, and here the reaction takes place in acidic medium in the presence of H plus. Remember this difference. Okay, so when coupling reaction with phenol takes place in basic medium, whereas in this case like around 9 to 10 degrees Celsius actually, and with 9 to 10, the pH will be between 9 to 10 with phenol, and with aniline the pH will be 4 to 5, like that much acidic pH is required there, and the temperature is 0 to 5 degrees Celsius only in both the case. Here we get AR and double bond N, C6H4OH, and in this side we get NH2. With aniline we get NH2, C6H4, C6H4N, double bond N, AR. Okay, so these reactions are called coupling reaction. That completes chapter amines also. Next we have simple chapter, that's most of this one is theory. We are not going to discuss much about biomolecules, just let's go through all the points once. Here in biomolecules, Yes, para-amino azobenzene. It's a yellow color dye, orange color dye. Very good. Okay, dye formation, coupling reaction, dye formation takes place. So in biomolecules, we have first one we have is carbohydrates. In carbohydrates, wait a minute. So let's take only few minutes, within 20 minutes, I'll 20 to 25 minutes, I'll wind up this chapter, biomolecules. So what are these carbohydrate? Carbohydrates are nothing but these are optically active polyhydroxyaldehydes or polyhydroxyketone. Many OH groups will be present. So these are classified into monosaccharides, disaccharides, polysaccharides, like that. Monosaccharide means we cannot hydrolyze that one further. They are the final units. And disaccharides means on hydrolysis produces two monosaccharide units. Polysaccharides means they produce many monosaccharides units on hydrolysis. And here we have this one, structural elucidation of glucose. So in structural elucidation of glucose, the first reaction which we have is, first thing which we have is these aldehydes, sorry, not aldehyde, glucose. Okay, CHOH 4 times CH2OH. So how it was determined? It contains 6 carbon atom. It is treated with hydrogen iodide. When glucose is treated with hydrogen iodide, it formed N-hexane. It formed N-hexane. This indicates 6 carbon atoms are linked in straight chain. Okay, the first thing is the molecular mass is determined by spectroscopic technique, and when it was treated, glucose was treated with hydrogen iodide, we got N-hexane, which indicates all carbon atoms are attached in a straight chain. And when it is treated with NH2OH, it forms oxime. Okay, with hydroxylamine, it formed oxime. What this indicates? Oxime formation. It presents, oxime formation indicates the presence of carbonyl group. Carbonyl group with hydroxylamine will form oxime. Here also we are getting oxime. So this indicates one carbonyl group is present there. Next, when this one is treated with hydrogen cyanide, HCN, so formed cyanohydrin. This also indicates the presence, cyanohydrin formation also indicates the presence of carbonyl group. Yes, carbonyl group is indicated here. And next we have is bromine water. When it is treated with bromine water, when it is oxidized in the presence of bromine water, it produced gluconic acid. Gluconic acid was produced. This indicates aldehyde is present. So oxidation of glucose in the presence of bromine water produced gluconic acid. This gluconic acid formation indicates the presence of aldehyde group in the given molecule. And when this is treated with acetic anhydride, CH3CO twice O, it formed glucose pentaacetate. Glucose pentaacetate. This glucose pentaacetate formation indicates the presence of 5 OH groups. Okay, glucose pentaacetate indicates the formation of, presence of 5 OH group. And when it is oxidized, glucose is oxidized in the presence of HNO3, it produced glucaric acid, which indicates the presence of primary alcohol functional group, primary OH group in the compound. So these are all the some like tests done to determine the structure of glucose. Now after all this, the structure of glucose was found given to be like this. A glucanic acid that further produces saccharic acid, CHO, OH, H, OH, H. CH2, OH. So this is the structure of alpha D glucose. It's because it is similar to D configuration in uh, this when OH group is present on right side from the below carbon atom, then that is called D glucose, that is less oxidized carbon atom. This is the Fischer projection formula. And see, though it is having aldehyde group, it didn't give 2,4 DNP test, and it does not form hydrogen sulfide when we add sodium hydrogen sulfate. So this indicates CHO group is present, but that CHO group is not free. So by seeing this cyclic, they told, okay, this is not open chain structure, this has cyclic structure, and cyclic structure of glucose was also given, where first carbon atom is attached to fifth carbon atom through oxygen linkage. And I'm writing Harvard projection formula for alpha D as well as beta D glucose. Just check the structures. H, OH, OH, H, H, OH, CH2, OH and H. This is structure of alpha D glucose. And in beta D glucose, we have only one difference in only one carbon atom. So configuration will be changed in only one carbon atom. Yes, on alpha carbon atom, OH will be down. This is beta D glucose. Sorry. OH will be upside here. H will be, other configuration will be same. This is beta D glucose. Beta D glucose structure. So alpha D and beta D, since we have change in configuration at only one carbon atom, that's called anomeric carbon atom. These are called anomers. On first carbon atom is called anomeric carbon, and on anomeric carbon atom we have configuration change. Configuration is reverse, that's why they are called anomers. Next, in this one, what else is important? Yeah, what sucrose is a, what are the monomers of sucrose? Sucrose is made up of alpha D glucose and beta D fructose. Alpha D glucose and beta D fructose, that these two are monomers of sucrose. Then if you consider maltose, Just if you say glucose, that's not okay. Here we have to say alpha, proper, their configurations also. Alpha D, beta D, whatever it may be. Okay, maltose. What are the monomers present in maltose? It is made up of 2 alpha D glucose. It is made up of 2 alpha D glucose and one and C1 to C4 glycosidic linkage will be there in maltose. Remember this, C1 to C4 glycosidic linkage of 2 alpha D glucose. Okay, then one more is lactose. Okay, consider one which is of lactose. Lactose is also called milk sugar. Milk sugar. So what are the, it's also, all these are disaccharides. What on hydrolysis, what are the monosaccharide units we get from lactose? One is beta D galactose and beta D glucose. Beta D galactose and beta D glucose are the monomers of lactose, and they are linked by glycosidic linkage of C1 to C4. C1 of galactose and C4 of glucose. So that's about disaccharides. And if you have polysaccharides also. In polysaccharides we have two example. One is starch. Starch. And see, starch contains two main things. It consists of two components. One is amylose, and another one we have is amylopectin. Amylose and amylopectin. So amylose are soluble in water. Where starch is present, starch will be mainly present in plants. Starch is mainly present in okay, starch is mainly, it's a food storage unit in plants. It's a polymer of alpha D glucose. Alpha D glucose will be present, and it is it consists of two components. One component is, as I told, it is amylose. So this is soluble in water. Amylose is water soluble, and around 15 to 20% of starch consists of amylose. 15 to 20% of starch consists of amylose. It is a long unbranched chain. Amylose is a long, since there are no branches, it is soluble in water. Long unbranched chain. Here there might be around 200 to 1000 alpha D glucose unit can be present. Okay, so these are again 1 to 4 glycosidic linkage will be there. 1 to 4 glycosidic linkage will be there. So that's about amylose. Amylose are water soluble. 15 to 20% of starch consists of amylose. It is a long unbranched chain. Okay, there will be no branches. That's why it is soluble, and it consists of around 200 to 1000, whatever may be the number of alpha D glucose units, and there will be one C1 to C4 glycosidic linkage will be there in this one. And if you take amylopectin, in case of another component, amylopectin, this amylopectin is insoluble in water, insoluble in water, and it is the major constituent of starch. Around you can say 80%, 80 to 85% starch consists of amylopectin only. It is a branched chain, not straight chain. Branched chain of alpha D glucose units, and here the linkage will be C1 to C4, C1 to C4 glycosidic linkage will be there, and the branches occurs at this forms straight chain, in straight chain C1 to C4 linkage, and C1 to C6 branch linkage will be there. C1 to C6, I mean carbon number 1 and carbon number 6 glycosidic linkage will be there. So that's about amylopectin. Okay, so amylopectin and amylose and amylopectin. Yep, these are components of starch. Next, if you come to cellulose, it is also a straight chain polysaccharide. It consists of only beta D glucose. It consists of beta D glucose. These are also joined together by C1 to C4 linkage of glycosidic bond between them. So that's about glucose. And glycogen is also present. Glycogen is also, it's called animal starch. It is a main constituent of human liver. Okay, so that's about carbohydrates. Next, if you come to proteins, if you take protein, so what are proteins? What are the main constituents of protein? These are the polymers of alpha amino acids. These are polymers of alpha amino acids. These are alpha amino acids. The structure is like this. NH2 at alpha position, amino group will be there. This is alpha position, alpha amino acid. Polymer of alpha amino acid is nothing but proteins. See, depending on number of NH2 and carboxylic groups, there are neutral amino acids, acidic amino acids, and basic amino acid. If COH group is more, then that comes under, like more than one COH group is that, then they come under acidic amino acid. If NH2 group is more, they come under basic amino acid. I'll write one or two examples for each. And you have to remember this example because the name will be given. This is example for which type of amino acid. You will be asked to write that one. Acidic amino acids, example you can take glutamic acid or aspartic acid. Okay, and basic amino acid example you can take is of lysine, then histidine, or you can take arginine also. These are example for basic amino acids, and there are some amino acid where equal number of NH2 and COH group will be there. They are called neutral amino acids. Neutral amino acid. Example glycine, alanine, valine, etc. See, based on their synthesis, they are classified into essential amino acids and non-essential amino acids. Essential amino acids are the one which you need to take through diet because they are not synthesized in our body. We want it through our diet. Those are called essential amino acids. Essential, one minute. Yeah. Essential amino acids. Which are the examples for essential amino acids? Lysine is an example for essential amino acid. Leucine, uh, leucine, valine, isoleucine, arginine. These are example for essential amino acid. These essential amino acids are not synthesized by our body. You have to provide it to your body through diet. And next one is non-essential amino acids. Non-essential amino acid. These are synthesized in our body. No need to provide them through diet. Okay, so example for non-essential amino acids: alanine, glycine, then glutamic acid, aspartic acid also, that's also example for non-essential amino acids. So that's about based on synthesis, their classification. And see, they form these amino acids are CH, C double bond O, OH, NH, 2. So in aqueous solution, they exist in the form of Zwitter ion. Zwitter ion means both positive and negative charges will be present in the same molecule. So such type of compounds are called Zwitter ions. They exist in Zwitter ion form. So that's about amino acids. And 1 minute, one point is that's isoelectric point. What are isoelectric point? Isoelectric point. So this is the pH at which your Zwitter ion neither migrate towards cathode. It remains neutral. It will not migrate towards cathode nor migrate towards anode. So that point is called isoelectric point. So that's about amino acids. And different amino acid, two different amino acids are linked by peptide linkage. Peptide linkage is a linkage between carboxylic acid of one amino acid to amine group of another amino acid. It will be like this. The structure will be like this. That is peptide bond, C double bond O, OH plus removal of water molecule takes place between acidic group of one amino acid and basic group of another amino acid, and that linkage is called peptide linkage. So if two peptide linkage, that means three amino acids are joined to form two peptide, that's called dipeptide, tripeptide, like that we have classification. And if I come to protein, we have fibrous protein and globular protein. Fibrous proteins are like a chain thread like structure which are parallel, held together by hydrogen and disulfide bond. Proteins are divided into fibrous protein, and next one is globular protein. Here in case of fibrous protein, the strands are held in parallel thing, and there exists a hydrogen bond and carbon disulfide, sorry, not carbon disulfide, disulfide linkage will be there. Hydrogen and disulfide linkage will be there. If you take globular proteins, when these polypeptide chains coils, then we get globular protein. So it is a three-dimensional spherical structure, and these are soluble in water. For example, insulin, albumin, these are all example for globular protein. And if you take fibrous protein, we can give example of keratin and myosin. Keratin and myosin are examples for globular protein. And we have different structures of protein: primary structure, secondary structure. Primary structure are, in primary structure of protein, it gives sequence of amino acid. In which sequence amino acids are attached? Sequence of amino acid. And if you take secondary structure, so it's just secondary structure is formed because of coiling of that coiling of peptide chain. This coiling takes place in two ways. One is alpha helix structure and another one is beta plated structure. Alpha helix structure and beta plated structure. So in alpha helix structure, these coils are stabilized by, like, the coiling or the foldings are stabilized by hydrogen bonds. Hydrogen bonds stabilize this one. And like they look like this. So this is alpha helix structure. And if you consider beta plated, only one will coil like this, one strand will coil. But if you consider beta plated structure, in beta plated, like myosin, all these are myosin and keratin are example for alpha helix structure. And if you take uh, silk protein, where beta plated structure will be there, different strands, they are held together. Okay, there exists a hydrogen bond between different strands, that is beta plated structure, like this. It's not planar, they will be having folding like structure, beta plated structure. So next we have is tertiary structure of protein. Structure, overall folding of polypeptide chain, that is how next secondary structure, how the overall folding will be there, that's called represented in tertiary structure of protein. So this tertiary structure is responsible for hydrophobic interactions of protein. See, van der Waals force of attraction will be there, disulfide bonds will be there, and ionic interactions will be there. This tertiary structure is responsible for all these type of responses of protein. And next one is, last one is quaternary structure. It's a spatial arrangement of polypeptide chains with respect to one another. Different polypeptide chains will be there. These polypeptide chains, how they spatially arranged with respect to one another, that is defined in quaternary structure of protein. Okay, when you heat it, or if you change the pH condition, if you change the temperature like that, then the structure of protein will be destroyed. Primary structure will not get destructed. Quaternary, tertiary and secondary structure will get destructed. That's called denaturation of protein. Okay, so that's about proteins. Next we have is vitamins. In vitamins, vitamin A, just we are learning vitamins and their deficiency diseases. So we left with only few things: vitamins and nucleic acids. In vitamins also we don't have much. So let me start with vitamin A. Vitamin A. So what is the chemical name of vitamin A? It is retinoids. The chemical name of vitamin A is retinoids, and it causes night blindness and xerophthalmia. Night blindness and xerophthalmia. Yes, retinol or retinoids. Anything is fine for vitamin A. Night blindness and xerophthalmia caused by vitamin A. And next one is vitamin B1. What is the chemical name of vitamin B1? Chemical name is thiamine. Chemical name is thiamine. And one more thing, vitamin A is fat soluble. A, D, E, K are fat soluble vitamins. B1 is water soluble vitamin, remember. And it deficiency causes very and loss of appetite. Loss of appetite. And next one is vitamin B2. This is called, the chemical name is riboflavin. This is also water soluble, and it deficiency causes anemia, then dermatitis, and it causes inflammation in tongue also. So these are something about vitamin B2. Next, if you consider vitamin B6, the chemical name is pyridoxine. The chemical name of this one is pyridoxine, and deficiency affects central nervous system, and it causes weakness also. The deficiency of vitamin B6 affects your central nervous system, and it causes weakness, insomnia, and anemia. So that's about vitamin B6. Then is vitamin H. Vitamin H is called biotin. Vitamin H is biotin, and its deficiency causes dermatitis. Dermatitis. And next is vitamin B12. Vitamin B12 is called cyanocobalamin. Cobalamin. And it causes pernicious anemia. Pernicious anemia. Left with only few more. That's vitamin C. That's called ascorbic acid. We all know about it. That's called ascorbic acid, and it causes scurvy. Deficiency causes scurvy. And vitamin D. Vitamin D is also called calciferol. Okay, there are two types. We don't want those two types of vitamin D, D1 and D3. So it causes rickets. Deficiency causes rickets. And next we have is vitamin E. Vitamin E is called, its chemical name is tocopherol. And vitamin E deficiency causes loss of fertility in men, and muscles will also get degenerated. Muscle degeneration will occur. Infertility in men is caused by deficiency of vitamin E. Okay, and last one is vitamin K. Its name, chemical name is phylloquinone. So deficiency of vitamin K, see, this causes blood clotting. Time will take for clotting of blood. Blood will if any injuries occur, blood will not clot properly. So that's about vitamins. Next we have is nucleic acid. Just I am giving the different types of nucleic acids and the classification. Within 5 minutes we are going to complete this one. Just see, biomolecules, it mainly involves theories, so you need to go through all these things once before your exam. These nucleic acids are polymers of nucleotides. Nucleic acid. So nucleic acids are polymers of nucleotides. These are present in all living cells and they play a very important role in transfer of hereditary character from parents to offsprings. Okay, they're present in all living things. These nucleotides are made up of three things. Nucleotides, they contains one pentose sugar. Pentose sugar may be, I'll explain that, and nitrogen base, it's not blood clotting deficiency. Time will take for clotting of blood if any injury occurs. It will not cause any deficiency. Nitrogen base and phosphate group. Phosphate group. So here pentose sugar are of two kinds. One is deoxyribose and another one is ribose. Ribose sugar and deoxyribose sugar. And in nitrogen bases we have purines and pyrimidines. Pyrimidines and purine. Which are purine bases and which are pyrimidine bases? Uracil and thiamine and cytosine. Uracil, thymine and cytosine, these three are pyrimidine bases. And if you go for purines, we have two purine bases. One is adenine, another one is guanine. And phosphate group will be like this: phosphate group attached to one oxygen and other O negative, like this. So from this negative charge it can be attached to any other groups. And if I consider nucleic acids are of two types. One is ribonucleic acid, another that's called RNA, another one is DNA, that is deoxyribonucleic acid. Next, Yeah, next, that's all about nucleic acid. Important things about nucleic acid. You need to go through all the structures of protein, what is the uses which helps in replication and all. Okay, so let's stop here. If you have any doubts in any of the topics here, comment me in comment section. I'll try to answer. I have covered most of the important topics in from all part 2, and this once the class completes also, if you have any doubts you can comment in the same comment section. We'll go through the comment and we'll reply you. Okay, so all the best for your exam. Do well, have confidence in you. Let's meet after exam. Okay, bye bye.